All right, ladies and gentlemen, you should have your classwork that we've been working on the last two class periods in front of you. And since you guys have slept a while and probably don't remember what we went over last class, I would like to help you set up a few of the problems to remind you of torque. That would mean that I want to set up problems 15, 16, and 17 with you. But while I'm doing that, I don't really want you to work them. I just want you to set them up. So what I am going to ask for you to do is to set your calculators to the side, set them on the floor, just set them somewhere. Be gentle, do not drop, and be ready to think about the concepts. On number 15 talks about Barry with his food and his tray. And what Barry is doing is Barry is actually holding his tray like this, and he has his thumb over here and his other fingers pushing up here. Okay. He then has his plate of food over here, yum yums, okay, all of his yummy yummy food, whatever that may be, and it is sitting there. What we're told is that his tray here, that all of this is on, is 0.5 meters long. You should be drawing this on your paper right now. We are told that it has a mass of zero point 0.2 kilograms. Well, if this tray has a mass of zero point 0.2 kilograms, then its force is 2 newtons because zero point 0.2 times 10, which is gravity, tells us its weight. Now that weight, if nothing else was on it, that weight would be centered in the middle of this tray. And so you should draw a force arrow, label it 2 newtons for the tray, and again put it right in the middle. Now it also says that it's holding this plate of food and that this plate of food that he has over here is 0.4 kilograms. If that's 0.4 kilograms, then its weight is 4 newtons when you multiply it by 10. And it is 0.2 meters from the right edge. So we're going to come over here from the right edge and we're going to measure over and we're going to say it's 0.2 meters. All right. Now it says that he's holding it up with one hand on the left edge and he's using his thumb. So this thumb right here is becoming the fulcrum. It's the pivot point. So everything pivots along there. And then he pushes up with his fingers. So his fingers are pushing upwards right here. And they are a distance that's 0.1 meters away. Now what we're asked to find is this upward force right here. We want to find this force of his fingers to keep it all balanced. What we need to understand is this force right here is going to cause a torque. So we're going to call it the torque of his fingers. The weight of the tray here in the middle causes a torque as well, and we're going to call it the torque of the tray. So we're going to label it torque T. And then over here, our plate of food also has a force, and it's going to cause a torque, and we're going to say it's the torque of the plate. Now, all three of these torques, torque of the food plus torque of the tray plus torque of the plate, must equal 0 because that's satisfying rotational equilibrium. So when we do this, we always are going to look at, if you remember, that torque is force times lever arm, and lever arm is the distance from the fulcrum, which we have drawn here in this picture as a green triangle. So if we start with our torque of our fingers, we do not know the force of our fingers. That's what we're trying to find. But we do know that it is 0.1 meters away from the fulcrum, so that's our R of that torque. We're going to add that to our tray force. Now our tray force is in an opposite direction as our finger force. So we're going to make it a negative 2 newtons because it's going down. And the distance from this green triangle to this black vector is going to be half of the tray. Half of the tray is 0.25 meters. Remember, the whole tray was 0.5 meters, and we put that vector in the middle. And so that means that that force vector is at 0.25 meters. We're then going to add that to the plate of foods force, which is 4 newtons. Again, it's going down, so we're going to make it negative. And the distance from this green all the way over to here where this vector is going to be 0.5 minus 0.2, which should tell us that the distance is 0.3 meters. All of this has to equal 0. So what you should be able to do now is you should be able to use algebra to solve for your F, your force of your fingers. I don't want you to solve right now. I just want you to have this set up on your paper. If the sub needs to pause this so y'all can make sure you get this on your paper, then do that. And otherwise, we're going to move on to the next problem. So don't work it out, calculate it yet. You can go back and do that in a little bit. Number 16. Number 16 is talking about a baby mobile that sits across a baby's bed and it hangs. You hang stuff from it so that they can look up at it. You don't want this to fall down on the baby. So the thought process is any weight that's pulling it down has to be canceled out by a force pulling it up. So that's the thing to think about. Now we're told that they hang, a toy sailboat. And we're going to hang it 0.01 meters from this left edge. And so this is going to be our sailboat over here. And our sailboat is 0.02 kilograms. So when we change it to newtons, we multiply it by 10 and we'll get 0.2 newtons for our sailboat force. We're then told that we come from the right edge and we come over 0.2 meters and we are going to have a toy truck. So this is our toy truck. Now our toy truck is 0.015 kilograms. So when we multiply that by 10, we get 0.15 newtons. Now these are the two forces that are pulling this mobile down. We are told that the mass of this black bar that these are hanging on is negligible, which means we don't need to take it into account for calculations. But we are also told that this whole bar is 0.5 meters long, and we will need to know that. Now what we don't know is that if these forces are going down, so we have the sailboat force and we have the toy truck force, they're going down. That means they have to equal the force of the string that's going up. So we have 0.2 newtons plus 0.15 newtons, which will then have to equal 0.35 newtons going up. So somewhere along here, and notice I didn't attach it to the black bar in any way, we have a force of 0.35 newtons going on because it's not falling down on the baby. So it's going to be balanced out. What we need to know is where do we attach that black vector? And that's what we don't know yet. So the first thing I told you to do on torque problems was to draw it, which we've done. And the second thing I told you to do was to know where the fulcrum is. Well, right now we don't have a pivot point. And when you don't have a pivot point, you're going to need to make one in the problem. And you can make it anywhere you want, but the easiest place to put it is on one of the ends. Pick one or the other. Doesn't matter which one. I am going to, for simplicity, just put it over here. If you want to put it on the other end, you can. That's not a problem. So it is all an option for you. But I'm just going to make up the fulcrum and I'm just going to put it right there. Okay. Now what I'm going to do is I'm going to say that the torque of my sailboat and the torque of my string and the torque of my toy truck all have to equal 0. So I'll go back and I'll say torque of the sailboat plus torque of the string plus torque of my toy truck have to equal 0. If that's the case, now I can go back and I can figure out force and distance for each one of them. The force of the sailboat is a negative 0.2 newtons because it's going down, and it's a distance of 0.01 meters from my fulcrum, which is my green triangle. I add that to the force of my string going up, which is 0.35, and it's positive newtons because it's going up, but I don't know that R, and that's what I'm trying to solve for. I don't know how far it is from that fulcrum, so that's my big question mark. Then I'm going to add that to the force of my toy truck, which is a negative 0.15 newtons because it's going down, and multiply that by what is the distance from this green triangle to this vector? Well, it is 0.5 minus 0.2, which means it's 0.3 meters. All of this needs to equal 0. Again, we've set it all up. Now it's algebra, and you should be able to solve. Don't solve right now. I want to set up number 17 before we go on. But make sure, if you need to pause this so you can get this written down, then do so now. Going on to number 17. Number 17 is talking about two paramedics, and they are rushing a man on a stretcher to an ambulance, and we want to know how much force each one of the paramedics is applying to keep the man horizontal. So here's our stretcher, and we are told that our stretcher is 2.6 meters long. Okay. We're also told that it has a mass of 3 kilograms. So if we're just talking about this stretcher and its mass is 3 kilograms, then that means its weight is 30 newtons. And I'm going to put that right in the middle. And the reason I'm going to put it right in the middle is because that's where its center of mass would be. That's where all of this force would kind of be represented. And so that's why we draw that arrow there. Now, you can make Orrin on either side. You can make Anita on either side. You just need to pick a side for each one of them. I'm going to put Orrin here, and he is applying an upward force to hold this stretcher up. Then I'm going to put Anita over here, and she's also applying an upward force to hold this stretcher up. Again, you could switch where Orrin and Anita are. That is all up to you. We are also told that the man on this stretcher is 60 kilograms, and his center of mass is 1 meter away from Anita. So what we're going to do is we're going to come 1 meter away from her, and we're going to draw a line to represent his weight. Okay, his force. Now, he has a mass of 60 kilograms, so his force is 600 newtons because you take 60 times 10 to find his weight. Well, this is one of those problems where we need to think about the ups have to equal the downs, and then we have to think about rotational equilibrium being satisfied as well. So we're going to say the force of Orrin plus the force of Anita has to equal the force of our stretcher plus the force of our victim. If that's the case, then the force of Orrin plus the force of Anita have to equal our 630 plus our 30 newtons. Or excuse me, 600. My bad. I was jumping the gun. So it's 630 newtons that these two have to equal. They do not have the exact same force though, because more of the weight is concentrated towards Anita, then she's going to have a different amount of force to keep him horizontal than Orrin is. So we've satisfied by writing this expression up here. We've satisfied translational equilibrium partially. Now what we need to do, though, is we need to talk about torques. And in order to do that, we've drawn our picture, but we need a focal, or not a focal point, a fulcrum. We can't solve for two things at once. So we have to decide we're either going to solve for Orrin or we're going to solve for Anita. I'm going to go ahead and put my fulcrum right here, which means I'm going to take Orrin out of the equation for a little while. And I'll come back to him later. But for now, I'm going to take him out of the equation. I'm going to solve for Anita. She's going to be the one I focus on right now. So I will have a torque here for my victim. I will have a torque here for my stretcher, and I will have a torque here for Anita. If that's the case, I need to do that in blue. There, color coordinate that. So then the torque of my victim plus the torque of my stretcher plus the torque of Anita all have to equal 0. So this is going to the rotational equilibrium. So now the force of my victim, oh, and I did those backwards. Sorry, guys. Let me rearrange my little subscripts. This one's going to be the torque of the stretcher, and this is the torque. Sorry, gang. This is the torque of the victim. Okay. Which will also change these. Sorry, color coordinating ended up causing a problem. My bad. So, my stretcher itself had a force of 30 newtons. Then my distance from the fulcrum to there is halfway, because it's in the middle of the stretcher, which would be 1.3 meters. Then I'm going to add the torque of my victim. And the torque of my victim, oops, I forgot something else. There should have been a negative on that 30 because it was going down. The force of my victim is a negative 600 newtons because it's going down. And the distance from this fulcrum over here to here is going to be 2.6 subtract 1. So that makes this 1.6 meters. We then have our force of Anita, which we don't know, and our distance from here to here, all the way across, is 2.6 meters. All of this has to equal 0. This will allow us to solve for the force of Anita. Once we know the force of Anita, we can take that force value and plug it in up here and solve for the force of Orrin. That would allow us to solve for the force of Orrin. So once you find this number, bring it up here, plug it in, and use this equation to solve for Orrin. But you always have to take one of the sides out when you want to solve for two forces at once. Okay, because you can't solve for them at once. So you have to take one out, solve for one, and then use it to solve for the other. Now what you need to do is you need to get those calculators, solve the remaining, calculate these 3 problems, and finish 1 through 17 completely. All the answers are posted on the board for you to check 1 through 17. Then turn it in. And once you turn it in, you'll need to pick up the additional problems and work on those in class, which you'll do problems 1 through 10 of the additional problems. But go ahead and finish these practice problems first. Be good and work together. You guys can do it, and I'll see you on Friday.